Good evening to everyone and welcome to this lecture, which is for the Herschel Society and the Visual Arts Group at the Bath Royal Literary and Scientific Institution, the BRLSI. I'm Tony Symes and I organise the lectures for the Herschel Society. Well, this is, as I say, being done in partnership with the Visual Arts Group. Now, the first thing I have to tell you is please note that this lecture is being recorded. Now, during the lecture, we want the audience to be on mute and also to have their outgoing video off, because that's going to help with bandwidth and we don't want extraneous noises. You can turn your audio and video back on as you wish at the end to take part in the Q&A session. Now, if the worst happens and Zoom stops working for you, then restart everything and we will make sure that you get readmitted to the lecture. During the lecture, if you have a question, you can put it into the chat channel and your question should be answered at the end. And if you afterwards you have another question, this lecture will be available on the BRLSI's YouTube channel, and you can add questions to the YouTube channel, which will be answered later. Now, a few words about our next lecture. This is the Caroline Herschel Prize Lecture, which is awarded annually to a promising young female astronomer and is supported by the Herschel Society, the University of Bath, and the Royal Astronomical Society. This year, it's been awarded to Dr. Rebecca Smethurst, who is an astrophysics research fellow at the University of Oxford. She'll be lecturing on supermassive black holes, the ultimate galaxy killers. This lecture is going to be about the discrepancy between modeling, computer simulations, and actual observations, and the attempt to reconcile them. This lecture is going to be on Wednesday, the 18th of November at 7 p.m. Registration for the lecture is free. This is not a BRLSI lecture. It's being done, as I said, through the University of Bath, and it can be, registration can be done through the events page of the Herschel Society website. And there's much more information there than I can give you now. So if you're interested, please go to the Herschel Society website and read about it there. Now, it gives me great pleasure to introduce our lecturer this evening, Dr. Bob Fosbury. He was based at the European Southern Observatory, the ESO, near Munich, and he worked for the European Space Agency as part of their collaboration with NASA on the Hubble Space Telescope since 1985. During the latter part of this period, Bob served on NASA's ad hoc science working group and ESA's study science team as they developed the instrument concepts for the James Webb Space Telescope, which is the yet to be launched next generation space observatory. He's now an emeritus astronomer at the European Southern Observatory and an honorary professor at the Institute of Ophthalmology at UCL. But before he starts, a few words from our visual arts partner, John Law.
Hello. In the spring, when Bob and I were designing the original poster for this talk, which we would show you if we were a bit better organized, this isn't it, I was intrigued by his reference to Leonardo, having observed the phenomenon that he took, one of the phenomena he talks about in 1510. So it seemed appropriate that the visual arts convener, which is me, should collaborate with the Herschel group in supporting and enthusing about this virtual version. I look forward to it, and I hope you will too.
Okay, if everyone can hear me, I shall start. I'm starting with this picture, which I'm sure everybody in the audience will recognize. And the point about this picture, it was painted in 1838 by a certain Mr. Turner, who had a certain interest in the colors of the sky, you might remember. Now, the color of the sky, in particular why the sky was blue, was a problem that had been addressed many times during the previous several millennia, with no success in understanding why the sky was blue. Now, one of the people, and the main person who cracked this problem, was Lord Rayleigh, J.W. Strutt, who was born 4 years after Turner painted this picture. So Turner did not understand the physics of the colors of the sky, but I must say he did a remarkable job of representing the colors that he saw. And I went through a little exercise, and I computed the colors of a twilight sky like this using my mathematical model of the colors of the sky. And I overlay a palette of my computed colors on his picture. Now, the characteristic of my computed colors is that they will be somewhat more saturated than the colors that Turner chose to paint. And there's a physical reason for this. It's that my computation is quite a simple one, and it doesn't take account of the mixing of various layers of the atmosphere which contribute to the color of a particular part of the sky. And so the fact that Turner's colors are somewhat less saturated, not very much, is I think well understood. But it struck me that it was a remarkable convergence between his appreciation of the sky colors and his wonderful representation of them and the way that we understand the sky colors now. But he didn't, of course, have access to that understanding. Now, I hope you recognize, some of you at least recognize my reference to 2001: A Space Odyssey here. So 182 years after Turner painted that picture, Rayleigh's fish, whom I will explain to you, actually I have Rayleigh's fish here. I can put it in front of the screen. You can probably see that. Rayleigh's fish is made out of a certain kind of glass called opalescent glass, which is actually an extremely good analog model of the Earth's atmosphere. And it can be used to make the colors that I'm going to be talking about this evening. So the picture on the left is a picture of the either setting or rising sun from the International Space Station. And you can see the range of colors, the spectrum of colors, this way and this way, represented, mirrored in Rayleigh's fish. So Rayleigh's fish can look down and think, well, now we understand more about how those colors are formed, but it was a struggle. And indeed, it was a struggle. It went very deep into 19th century physics before the understanding was actually realized. And it involved a whole range of people, very well-known scientists, including Einstein, who was trying to figure out why the sky was blue and exactly how it all worked. Just dwelling a little bit on the material used to make the fish, you can buy in a lot of these sort of gift shops and stone shops, you can buy these little cubes or shapes of opalescent glass, which have remarkable properties. I mean, this is actually a set of these glass cubes in a bottle in water, and the water just matches, doesn't quite match, but it more matches the refractive index of the glass, and so it makes the cubes more visible. And if you illuminate these cubes from behind, so if I look at a light through the cubes, I get this wonderful sunset colors, the oranges and the yellows. And if I shine the light from my side of the picture onto the cubes, I get the blue sky. So exactly the same cubes illuminated in a different way. And this is actually a very good representation of the basic physics of the coloring of the sky. You might want to try and get one of these and experiment with them. They're great fun. And again, my model sky superimposed on top. So you can see I can compute these colors fairly well using a simple model of the sky. So what I'm going to talk to you about during this talk, I won't say tonight because I don't think all of you are in the same time zone, so I'll be careful about using day and night. The first topic, and it'll get us started, is about extinction. That is the color of the sun. You're all familiar with the fact that the sun looks pretty white when it's high in the sky, but when it's setting, it's either yellowy orange or even red under some circumstances. And so we're going to explore what is the physics that produces the changes of color as the sun changes altitude in the sky, in a clear sky. The second part of the talk is the next bit of the argument, and that is, how do we actually paint the sky with the sunbeams that are stolen from the sun? So we can fairly easily understand the color of the sun as seen through the atmosphere, but understanding the color of the sky seen at different times and in different directions is the next stage in complexity of the process, if you like. So I'm going to be talking about scattering and the painting of the sky with stolen sunbeams. Then we'll move on to something which is very important in coloring the sky, but is not widely known about or understood, at least in my experience. Not even all the physicists I know understand why the sky can be particularly blue at twilight. So I'm going to talk about the elephant in the room, ozone, and the blue hour. Now, I'm sure many of you, especially the artists, will have heard of the blue hour and the magic of the coloration of the twilight and the feeling of romance or whatever that is engendered by painting in the blue hour. We'll explain the nature of the blue hour and what actually causes it. Then we have a section which is really for fun, and if we run out of time, I can leave some of it out, but it's talking about the colors of clouds. The solar and lunar eclipses are very important in allowing us to explore the Earth's atmosphere. And indeed, lunar eclipses are a very good analogy of exoplanet transits. Now, this is when a planet in another solar system passes between its star, its home star, and us. And so we see the shadow of the planet or the silhouette of the planet as it crosses the star during its transit. And some of that light will pass through the atmosphere of the planet. And we can actually, nowadays, we can detect that fraction of the light and analyze it and learn something about the exoplanet atmosphere. Now, it turns out that a lunar eclipse is essentially the same geometry as an exoplanet transit. So we use lunar eclipses to practice this really rather difficult astronomical problem of studying exoplanet transits. So I'll talk a little bit about that. And then the end part is actually painting the sky at night with color. So I'm going to be talking about etching the sky with invisible radiation, something we call the air glow. And you need a very dark sky to see the air glow with the naked eye. It's not very bright, you can't see the colors very well, but you surely can photograph it with a modern digital camera. And I'll show you some of the very spectacular pictures of the air glow taken from our observatories in Chile in the Atacama Desert at night, where you can see the brilliant colors of the air glow. They're really quite spectacular. So don't leave before the end, because the best bit's the last few slides. Right, let's get down to work. Now, I'm an astronomer by trade, and I spend most of my time trying to get away from the atmosphere. In fact, we launched Hubble to get above the atmosphere so we didn't have to look through it. And I like to show this picture. This picture was taken especially for us by Claude Nicollier, who was one of the European Space Agency astronauts on the space shuttle. Several missions he flew. He flew on the servicing mission to Hubble in 1999. And as it was flying across the the coast of South America. This is Peru up here, and this is the Chilean coast stretching down towards Tierra del Fuego in the Antarctic. And we're at the moment over the Pacific Ocean. We see the clouds over the Pacific, but the clouds rarely venture across the foothills of the Andes. There's a coastal range of mountains here which trap the clouds over the ocean, and they very rarely come up and over the coastal range. So we have the European Southern Observatory, have three major observatories in Chile in the Atacama Desert. One is way down here, about halfway towards Santiago, which is well in the south. Our very large telescope, which is fairly close to the coast here, about 2,800 meters in altitude, is very, very good for optical astronomy, one of the best sites in the world. The other observatory, which is our submillimeter observatory, it's an international collaboration, including the North Americans, the Japanese, the Taiwanese, and Europe. This is a very spectacular observatory, but it's at 5,200 meters on the Altiplano. So you can't really go there with any ease. You have to have medical checks, and you certainly don't want to spend much time up there. The buildings up there are pressurized, so you can go in the buildings. But the observatory is operated from much lower altitude, down here somewhere. So we spent a lot of time and money escaping from the atmosphere, but we still look through it and we need to understand it. Now, the nature of the spectrum, the visible spectrum, is so important for this talk that I'm going to spend a minute or two explaining what I mean by the spectrum. And you'll be familiar with the rainbow colors of the spectrum. I'm going to leave this this pattern up here as I step through the spectra of a number of different light sources, so you can see what the spectrum looks like and what it tells you. And the axes of the plots here, on the left is the brightness of the light in energy units. We need to know what the energy units are. And on the horizontal axis here is the color, or the wavelength, measured in nanometers. So here we spread from about 300 nanometers, which we can't see. We start seeing it around 400 nanometers, and we see up to a little over 700 nanometers. But then we get the near infrared up here, which we can't see. And this spectrum here, this plot here, the increasing intensity into the infrared, is an old-fashioned, now it seems remarkably old-fashioned, tungsten filament lamp, a light bulb in common language and parlance. And you can see why these light bulbs have been replaced by more modern lights, because they don't emit very much light in the visible spectrum. They emit very little blue, they emit more red, but they emit most of their energy in the near infrared, which we can't see. So all it does is radiate heat. Now, if we start looking at more modern lamps, the orange curve here is a modern LED. You're going to have some of these in your house. You'll probably see them outside as street lamps. They only emit really in the visible spectrum. That's to make them very efficient, so they don't waste energy outside what you can see. But they're really rather peculiar shape. And you see this very, very strong peak in the blue. This is the result of the Nobel Prize for Physics in 2014, won by Japanese physicists who developed very efficient ways of making blue LEDs. And it's this blue LED which excites the phosphor in the lamp to produce the rest of the colors and make something which looks white. Now that's an LED of 4,000 kelvins, the color temperature, which they normally print on the bulb and on the bulb box these days. You can buy LEDs which are either whiter, bluer. This is a 6,500, it's a daylight LED. And you can also buy them which are somewhat more warmer in color, which actually means lower color temperature. Physicists and lighting engineers use the temperature scale in the opposite way, but never mind. Now, I'll just make an aside remark about this blue peak here, which appears in all of these very white LEDs, which we're surrounded by. This is extremely damaging to wildlife and indeed to humans. And we're very worried about this, and we have to find ways of changing it. It upsets many physiological processes, and it's very unfortunate that there's this tremendous drive to have white LEDs everywhere. It's very nice to see full color with a white street lamp, but actually it's very dangerous for wildlife, and it's actually somewhat dangerous to humans as well. A slightly more old-fashioned lamp, the old mercury high efficiency bulbs that you could buy, which were fluorescent bulbs, very much like the fluorescent tubes. They produce white light by producing a few bright colors, one in the blue, one in the green, and one in the red, and a few other bits of emission here and there. So they also produce the impression of white light, but they don't reproduce colors of carpets and clothes very well. And you'll be very familiar with that problem. A blue sky looks like this. It's blue, it goes up in the blue. This is the solar spectrum. These are all the absorption lines in the solar atmosphere you can see here, usually known as the Fraunhofer lines. That's what a blue sky looks like. A cloudy sky is less blue. It's still somewhat blue, but it's less blue. And it's, I've just matched the brightnesses up here. It's not necessarily fainter than a blue sky. And a twilight sky is very different. You can see a twilight sky has this big dip in the orange, and we'll come on to that later. That's very important. But this big dip only appears close to twilight. This is the visible spectrum, which I've isolated in white here in the middle. This is the part that we actually see, but in this plot, you can see what goes on outside the visible spectrum. And this is actually a representation of the three different receptors in your eye, which produce color vision. The short wavelength cones in the blue, the medium wavelength cone in the green, and the red wavelength cone, the long wavelength cone in the red. Now you'll see that the blue and the green eye sensitivities are fairly widely spread apart, and we have very good discrimination between greens and blues and all the shades in between. But in fact, the discrimination between the green cone and the red cone is really rather poor. So we have very little discrimination between different red colors. I'm sure you've noticed this, but these are our three receptors in our eye. And this is what we use to represent the colors that we see. Now, before I start talking about the sky, I should look at this history from the origin of the Earth 4.5 billion years ago to now. We didn't always have a blue sky on the Earth. It probably was very hazy and probably orangey for the first 1.5 billion years. And it was only when the plankton and the bacteria started producing oxygen by photosynthesis, and when that oxygen started migrating from the ocean into the atmosphere, that the atmosphere cleared. It was cleared by the effect of this, at that time, extremely toxic gas, oxygen, appearing in the atmosphere and oxidizing things in the atmosphere and clearing it out. So we haven't always had a blue sky, but we do now. And it was really cleared by the presence of the first oxygen produced by life. The Earth's early atmosphere probably contained methane, which, when it interacts with the solar ultraviolet light, would have produced this orange haze of hydrocarbons. And in fact, we can look in the solar system now, in particular at Saturn's moon Titan, which is probably a reasonable representation of what the Earth's atmosphere might have been like in those times. So you can see here the atmosphere of Titan with this thick orange haze at lower altitudes. So I said the first topic on my talk was to talk about extinction, and this tends to be a bit of physics, so I apologize to the artists, but try and concentrate and try and follow what I say. There are two processes that go on, and there are three principal ingredients. I've bolded the processes and I've italicized the ingredients. So the first process is the process of bouncing incoming sunlight from constituents of the atmosphere, mostly molecules, and this produces what we call Rayleigh scattering. I mentioned Lord Rayleigh in the beginning. He was the guy who figured out how this worked. And Rayleigh scattering produces the blue sky. Rayleigh scattering scatters blue light much more strongly than it scatters red light to the fourth power, or the minus fourth power of the wavelength. The other constituents which are always present in our atmosphere are aerosols. These are tiny droplets, tiny dust particles, and so on, mixed together, salt crystals from the ocean and so on, all very small. They also scatter more blue light than red light, but the difference is not so great. And a typical value of this number here for aerosols is 1.3 rather than 4. So it's a softer kind of blue scattering than the Rayleigh scattering. So aerosols and molecules are always present in the atmosphere, and they produce the blue sky. And the bigger droplets will produce the white clouds. We'll come on to that. So that process of bouncing light from molecules or aerosols is called scattering. It's like using a billiard ball to scatter other billiard balls around the billiard table. The second process is capturing light actually at specific colors or wavelengths and transforming that light into something else, usually heat. And we call this process absorption. That's where the light actually gets absorbed. The light itself is destroyed or transformed into something else. The energy is not destroyed. The energy is taken in some other form. There are many different absorbers in the atmosphere, but ozone is actually the most important for visible light. And that's important to remember. There are many absorbers at other wavelengths in the atmosphere, but ozone is the only one that really has a profound effect on the color of the visible color of the atmosphere. Now, I hesitate to show this to artists, but my artistic skills are rather limited. I kept my original sketches. These are the sketches I made when I was thinking about this talk about 9 months ago now, and I kept them and used them to introduce these various sections. So talking about extinction, okay, we have the sun outside the atmosphere. We have me standing on the earth here, dancing. And as the sun comes through the atmosphere, it passes through a column of atmosphere, getting denser and denser as it goes towards the surface. And it's the Rayleigh scattering of light out of that beam sideways, not just at right angles, but in all directions, forwards, backwards, and sideways, that makes the blue sky. So you steal some of the blue light from the sun coming in through the atmosphere, you send it sideways and it makes the blue sky. Simple, okay? And because you've stolen some of the blue light, the light that reaches the ground is somewhat redder than it was before because you've taken the blue away. So if I'm standing here looking at the sun, it looks a little bit redder than it would look if you're an astronaut outside of the atmosphere. Okay, so that's the process of scattering. Now, extinction is the sum of scattering plus absorption. Now, I've mentioned absorption. I haven't talked much about it yet, but extinction is this process that changes the color of the sunlight as it comes through the atmosphere and reaches the ground. And as I emphasize again, visible extinction is usually dominated by the scattering rather than absorption. Not true if you look in the infrared or you look in the ultraviolet. But now this is my first real spectrum. So remember, blue and ultraviolet down this end and red at this end. This is actually further into the infrared. You can see the visible spectrum here. The thin gray line up here is the spectrum of the sun outside the Earth's atmosphere. This is what the astronauts would see from the space station, okay? And you see, as you go down towards the bluer wavelengths, this is the blue light here is the spectrum of the sun seen at an altitude of about 30 degrees. So a good winter sunlight at noon, about 30 degrees, will be redder than the sun outside the atmosphere. And you can see the way the extinction progressively removes more and more of the blue light as you go through the visible spectrum. And the blue line here is my extinction model. This is my mathematical model of the extinction of the atmosphere. The red line here is actually a measurement made with one of my spectrometers, which I have, I can show you, make it more real. This something that looks like a big exposure meter. It receives the light here, shows the result on the screen, and it measures the energy at different colors in the visible spectrum. Very useful device. So the red line here is the measured spectrum. You see it's a pretty good match to the model I have, or the model is a pretty good match to the measured spectrum. You begin to see some absorption here. This is absorption due to water. And here I've continued with an infrared spectrum where the water absorption gets really strong. You see these strong bands here. I've marked at the top here H2O. These are the water bands in the infrared spectrum of the sun. There's another one down here as well. Water absorbs very strongly in the infrared. The decreasing absorption as you go towards the visible spectrum and the blue is the reason that water in deep, clear pools with light stream beds looks blue. Swimming pools look blue. Water is blue if you look through depths of clear water which are more than about 1 meter. So when you get deep in the ocean, the light is extremely blue, and fish have to adapt to that. And the blueness is produced partly by scattering, but largely by water absorption. Water absorption is minimum around in the blue here somewhere. So it's very, very transparent in the blue. And there are other absorptions here. We won't go into those now. Methane, carbon dioxide, various forms of oxygen and so on absorb. But this is just to give you an idea of what extinction looks like. It's mostly scattering in the visible, and it's mostly absorption by molecules in the infrared. Now, before we move on to understanding the sky, again, I have to do a little bit of simple physics here to explain it. This is an important concept. We have a concept called an optical depth. Now, you'll all be familiar with what this looks like. If you go out in the mist, if you went out this morning in Bath and looked out, you would see a mist around you, and the mist would inhibit the distance over which you could see objects. Now, maybe this morning when I went out, you could see maybe a few hundred meters into the mist, and then things became invisible. You just saw a whiteout. Now, when you can see the outlines of objects in the mist, that corresponds to an optical depth of 1. So this number tau up here, which I call the optical depth, will be a value of 1. And we have to understand what contributes to this optical depth. Well, I've already told you that one of the things that contributes to the optical depth or the absorption or the extinction is scattering from molecules. So I have a long column of air here stretching through the atmosphere. It may be kilometers or meters long, whatever you want. But this is a column of molecules of air, mostly nitrogen, some oxygen. And these molecules of air will scatter light sideways. So the light comes into the column, some light gets scattered sideways, and the light that comes out in the end is redder, as I showed before. Okay, so the strength of the scattering of an individual molecule of nitrogen or oxygen we call the cross-section, because in fact it's essentially just the amount of sky, the area of sky that's obscured by that little molecule. And we call that the Greek sigma, and it's measured in square centimeters. So we call it the cross-section of the for the scattering. That's the strength of the scattering. Now, it's important to remember that that scattering strength, sigma, depends very strongly on wavelength. I've told you it depends on the wavelength for Rayleigh scattering. It depends on the fourth power, the inverse fourth power of the wavelength. So it's a very strong dependence. So this scattering cross-section depends on the color. And that's the reason we see colors in the sky. So it's very important to understand that the scattering strength is not uniform everywhere. It does depend on the color. Now, the amount of scattering you get and the depth of color that you get will be proportional to the amount of material that the light travels through. So that's proportional to the length of this column, and it's proportional to the density of particles here. So we call this amount of material the air mass, and it's simply the density times the length of the column. And then going back to our optical depth is simply the product of all these three numbers: the strength of the scattering, the density of the particles in the atmosphere, and the length of the column. Okay. Well, I won't apologize for the mathematics. It's very simple. So tau equals 1, the optical depth of 1, which is where you just see the outlines in the mist, corresponds to a physical distance of what we call the photon mean free path, which means the mean distance, the average distance a photon will travel before hitting a scattering molecule. So that puts it in context. Okay, well, I'll make it seem a bit more real by moving on a bit, but a little bit more mathematics first of all. If you let this x be the optical depth, then the amount of light that transmits through a column depends in this way on the value of the optical depth. So when the optical depth is 0, down here, all the light comes through. As the optical depth reaches 1, about a third of the light gets through.
No, thank you.
And as the optical depth increases further, the amount of light goes down very, very rapidly. And so that's the mathematical form of the extinction. It decreases very rapidly with the increase in the optical depth.
Thank you.
And to illustrate what it looks like, this is just a photograph taken of the top of a cliff in Wales in a sea mist, and you can see the vegetation at the top of the cliff decreasing in visibility as you go along here, and the optical depth of 1 corresponds to a region around about here. Now, this is another example of extinction. This is taken of a setting sun in a rather turbid atmosphere. It's not completely cloudy. You can still see the outline of the sun. But this would represent a somewhat larger optical depth because you have a very bright source here. You can see through to optical depths of about 5 or 6 in light like this. Now, before we move on to looking at the colors of the sky, again, we have our familiar picture of the sunlight above the atmosphere. Our model of the sunlight with a sun 10, 20 or 30 degrees above the horizon, so a very visible sun. And these two lines here, the red line and the blue line. The blue line represents the blue sky, and the red line represents clouds in the sky. You'll see the blue sky is bluer than the cloud, but actually the cloud is bluer than the sun that you see, and in fact it's rather similar to the sun outside the atmosphere. And that's just because the sun has the atmosphere has stolen some of the sunlight to make the blue sky, and the process of stealing the blue sunlight leaves you with a somewhat redder sun, but the clouds absorb both the direct sunlight and they absorb the light from they're radiated by the blue light from the sky above them as well. So they mix some of the blue light back into the sunlight to make the clouds look generally bluer than the sun itself. And I'm sure you've noticed this on occasions as well. The clouds can be very white, much whiter than the sun, especially when the sun is lower down. Now, I've put this on an energy scale, but I've had to shift these blue and red lines up by a very large factor because they're very much fainter than the direct sunlight, of course. The other interesting thing is here, I've marked these green areas here in the far red. This is actually the reflection of vegetation on the ground back onto the undersides of clouds. When you look at the undersides of the clouds, you're seeing partly the light shining through the clouds from above, but you're also seeing the light coming up from the illuminated ground below. And that can be quite strong, a little bit beyond our vision. Our vision ends about here, so we don't see this with our eyes, but we can see it very strongly with infrared cameras. And you've probably seen infrared camera pictures of the landscape showing very, very bright vegetation. It also reflects back from a clear blue sky, actually, by scattering, and you can still see the vegetation reflectance in the blue sky. Now, before I talk about the sky, I just wanted to talk about the huge range of brightness we have to look at in the sky. If we look at the brightest sunlight, the radiation hitting the ground is about 120,000 of these units, which are units of visible light. So the brightest sunlight hitting the ground with a very high sun and a very clear sky is about 120,000 units. And that's 120,000 times brighter than the light under a thick storm cloud at sunset or sunrise. So the range of brightness in daytime is absolutely huge, and our eyes have to cope with this huge range. Even more when we go into nighttime, with moonlight, clear sky, we're roughly the same as this thickest storm clouds. So, you can see perfectly well in moonlight at night in the landscape. And so we go down to a full moon, quarter moon, starlight, clear moonless sky. Remember this because this is the conditions I'm going to show in the last slide that I show at the end of the talk. So that's 0.002 of these units. So that's very much fainter than full sunlit sky. And we go right down. So we've covered in this whole table of brightnesses, we've covered a factor of 1 billion. So 1,000 million times in brightness. And our eyes have adapted to this, which I think is worth considering. We don't use the same detectors in very dim light as we use in daylight. We use our rods rather than our cones, but we can still cope with an extremely large dynamic range. Now, my second topic was painting the sky. How do we form the twilight colors? Again, my cartoon here with the setting sun shining up and seen as a red or an orange setting sun. And we're looking towards the sun at twilight, and we see this range of twilight colors. And we see this very dark blue above us, and we see something called the earth shadow behind us on the opposite side of the sky from the sun. Understanding this process involved very many people thinking in the 18th and 19th centuries, and the people involved with this were people like Humboldt, Saussure, Tyndall, Stokes, John Herschel, Maxwell, Rayleigh, and Einstein. So this was a very, very hot topic in the late 18th and throughout the 19th century. It was a very important topic in physics. Now, what I want to explain here is an important concept for understanding the twilight colors, and that is when you shine light into the sky, when you shine sunlight into the sky, and you look at the colors coming from the sky, not directly from the sun, but from the sky itself, you have two effects going on. One is you have a source, that is the scattered light from the atmosphere. If you just imagine a little cube of atmosphere somewhere in the sky, and you're shining sunlight onto it, that little cube of atmosphere will scatter some light down towards your eye. And so that's the source of the light. That's the light bulb in the sky that's producing the light you see in a blue sky or a cloudy sky. It's scattered sunlight. And as this light is scattered towards you, it will suffer extinction in the same way that the sunlight suffers extinction as it comes from outside the atmosphere down to the surface, down to your eyes. So you have two terms in this. You have a source term and a sink term. So when you multiply these together, instead of having this extinction curve, which just uniformly goes down towards larger optical depths, here you have a curve which rises up to a maximum at an optical depth of about 1 and then drops again. Now, all this means is if you imagine looking up into the sky and looking at the light coming from the sky, that light is coming predominantly from a region where the amount of atmosphere that the light has traveled through corresponds to an optical depth of 1. Now, I'll show how that works in a moment. It's an important idea, and it explains the colors of the sky. So we have this conflict between making the sky brighter, the source, how much it scatters, and making it fainter again, how much light we remove from that skylight as it comes down to us. And it's because those depend differently on color that we can generate the different colors in the atmosphere. Now, I've just reminded you here, when light is shone into a turbid medium, that is a medium that scatters, most of the light that reaches you comes from regions where the optical depth is around 1. So this is how it works. This is a pair of pictures taken from our observatories in Chile. One is a sunrise on the right here, and the other one's a sunset over the Pacific with the clouds underneath. Very, very clear skies. You can see the moon in both of them, so you can infer where the sun is. The sun's down here in this picture, and the sun's over here in this picture. So we're going to consider light coming in from the side, from the sun, traversing fairly high in the atmosphere and coming up to some region of sky somewhere above us. We're the observer down on the ground here. The light is scattered here and it's coming down here. Now, the most of the light you get scattered up high in the atmosphere here will be in the part of the spectrum where the scattering is very strong. So the optical depth is large, but because you're high in the atmosphere, the density of the atmosphere is low, so you'll be traveling through a small amount of atmosphere in terms of numbers of molecules scattering. So the product of the scattering strength and the air mass, which I mentioned before, the number of molecules in the atmosphere, is about 1 for the blue high up in the sky. Now, if you travel somewhat lower in the sky, you're traveling through more atmosphere. So you have more scatterers. So in order to get the light scattered down to you, you have to go to redder wavelengths where the scattering is less strong. So tau is smaller and the air mass is bigger, but where you see the light coming from still has tau equals 1. And so you see this greenish blue light from the intermediate altitudes in the atmosphere. And if the light travels in very low through the atmosphere, you've got lots of atmosphere, lots of molecules, and so you have to move further into the red. So there you're seeing the red light getting through. So this number, the optical depth, is essentially the same for all these paths. But because the paths are so different in their content of atmosphere, the colors that you see are different. And this is simply the reason for the lovely range of colors that you see from high in the sky above the sun down through this lovely sort of slightly apple greenish color here down to the orange and eventually the red near the horizon at sunset or sunrise. Now, I mentioned the far side of the sun. When you're looking away from the sun towards the anti-solar direction, you get this wonderful shadow here. It's called either the Earth shadow or the dark segment. It's very noticeable when you have a very clear sky and the sun is setting, provided you can see the horizon. And this is actually, it has something called the belt of Venus above it, the pink light of the belt of Venus. And this is really the shadow of the ozone layer rather than the shadow of the limb of the Earth. And it's this wonderful metallic blue color here. In fact, it's very similar to the color of the zenith sky at twilight. It's this wonderful metallic blue color because of the ozone in the atmosphere, and we'll come to that in a moment. But this is a very lovely picture from Chile of the Earth shadow. For those of you who might be interested, these are the models that I use to make those swatches of color and understand how the process went on. And these are a sequence of models for small air masses in the violet and the blue, and larger air masses going through green, yellow, and red. So this is how the shape of the spectrum changes as you go from small air masses to large air masses. So the tau here is going from 0.1 to about 13 to produce these different colors. And all I did to make the swatches was to add together the light in these spectra in the blue band, the green band, and the red band. So that's how I converted my spectra to colors. A little bit about aerosols. We've talked mostly about Rayleigh scattering now because that's the predominant way of making the colors of twilight. The aerosols, depending on their nature, have different effects at twilight. They can make the shades very pastel, as this lovely misty twilight in the foothills of the Alps shows. Very subdued pastel colors. For certain types of aerosols, the skies can be quite lurid. This is the effect of smoke in California, photographed by a colleague of mine in the US. And you get this very lurid greenish, almost vomit colored sky here. And these are the effects of aerosols in the sky. Now, coming to ozone and the effect it has on the atmosphere. Ozone is obviously a very important molecule for us on the planet because it protects us from ultraviolet radiation, fortunately. And so it absorbs all the dangerous ultraviolet radiation. So it doesn't damage us, it doesn't damage the animals or the plants as well. It would damage everything if the ultraviolet reached the surface of the Earth. So it's an oxygen molecule, but it's trioxygen. rather than dioxygen. Normal oxygen in the atmosphere is just two molecules, two atoms together to form a molecule. But the ozone molecule is three oxygen atoms together. And it's really rather unstable. It's formed by ultraviolet light high up in the atmosphere, and it's destroyed by light very, very quickly. So it's, although there's a fair amount there, each individual molecule of ozone is very quickly being created and destroyed in the atmosphere. And if we look at the absorption of ozone, it's a very complex. Here again, we have a spectrum plot with the cross section here, rather than brightness, it's the cross section, it's the scattering strength plotted upwards here and the color plotted sideways here. You see the highest cross section is in the ultraviolet here, where the ozone absorbs essentially all of the ultraviolet radiation up to this color in the atmosphere, fortunately for us. Then there's a big dip in the blue where it's very transparent, but it can absorb again in the orange here. This is called the Chapuis band of ozone, and this is responsible for the colors of the blue hour and so on. And then the strength of the scattering decreases again as you go into the infrared. So those are the data I use in my model to compute the effect of ozone on the atmosphere. Just to show that it's really blue, this is a lovely picture of some liquid ozone. Liquid ozone is very difficult to produce, and it's also extremely dangerous because it's extremely unstable. It's very easy to explode it. So people are very careful when they make liquefied ozone. But it is this beautiful ultramarine color. It's a slightly reddish blue. And this is absorption in this Chapuis band of ozone. And it's this absorption which produces the color of the twilight sky and the color of the blue hour. And what happens at twilight is if we have the surface of the Earth here, we're standing here at sunset and the light is coming in from the setting sun. And the ozone layer here doesn't extend down to the ground because it would be very nasty for us. It's between an altitude of about 12 and 40 kilometers in the atmosphere, where most of the ozone exists. So the light shining through here travels a long distance through the ozone layer and then illuminates the high atmosphere above here. If we're standing here looking upwards, we're seeing a lot of atmosphere which is being illuminated by light that's traveled through the ozone layer. And that's what produces this very blue, steely blue, twilight blue sky. This was only really realized by this guy, Hulbert, in 1953, when he was trying to understand the color of the twilight sky using sounding rockets just after the war. They had a number of V2 rockets from the Germans after the war, and they were using them to try and understand what was going on in the upper atmosphere. And that was when he realized the important effect of ozone on the color of the twilight sky. And so we have this blue, this is a lovely picture I found on the web of the altitude of the sun and the sort of artistic impression of the colors of the light at different altitudes of the sun. So just before sunset, you get this golden hour, and sometime after sunset, you get the very blue illumination called the blue hour. And then we lose our color vision when we get down here. So we're not sensitive to color really at those points. So the golden hour and the blue hour. I can show you what it looks like, but before I do that, remember that when the sun is down here, the light is very dim and your eyes are losing their color sensitivity. And so you're seeing more and more with your rods rather than your cones, and rods don't give you much color sensitivity. And so you lose the vision. But if you take pictures with your camera set to daylight white balance in the blue hour, you will find indeed that the pictures are extremely blue. And I can show that here. This is a picture of the Mediterranean, actually on the Turkish coast, taken just before sunset, looking out over the sea. And you can see this lovely golden color of the setting sun. Now, the same scene taken about half an hour after sunset, and it's really, really blue. So the sky is blue, the sea is blue, and the light is blue. Everything is blue, and that's because of the ozone absorption. Now, I just put this in because some animals have to adapt to the very blue color of twilight skies. And the time when you're most subject to long periods of twilight is, of course, close to the Arctic or the Antarctic Circle. And there are really rather few animals that live close to the Arctic Circle, but one of them is the reindeer. And the reindeer has this amazing ability to change the color of this reflector within its eye. This is a reindeer eye being dissected. The retina's been removed, but this surface behind the retina, called the tapetum lucidum, the shining carpet, which in most animals is kind of a silvery reflector. Indeed, in a reindeer, in summer is a sort of silvery golden reflector, but in the winter, the reindeer has the ability to change the color of its tapetum to this beautiful deep blue, and that helps it see in the Arctic twilight, and it helps it see its predators against the snow because the light is very dim, but the light reflected from the snow is very blue because of the ozone twilight, and this gives it an enhanced sensitivity in the blue at twilight. Now, just to show the strength of this effect, we're looking at the spectrum again. This is brightness up here and color along here. The green line is the twilight as it would appear if there were no ozone in the atmosphere. So you remove the ozone and you get this strong peak in the green at twilight. But if you inject the ozone into the atmosphere, and at twilight, remember, the light travels a long distance through the ozone layer, you get this very strong Chapuis band absorption, which brings you down here. And so you've removed all of this buff-colored light from the sky at twilight because of ozone. And that energy absorbed by the ozone goes into splitting the ozone apart into a single oxygen and a coupled pair of oxygen, normal atmospheric oxygen molecular gas. And well, this is why I call it the elephant in the room. It's a very, very significant effect. Many people are not aware that it happens at all. And it does actually look with a bit of imagination, a bit like an elephant. So that's why I call it the elephant in the room. Sorry about that. Now, before I finish with the air glow, I just wanted to talk a little bit about shadows and eclipses. And again, one of my simplistic diagrams, you've got the sun here shining down onto a parcel of atmosphere somewhere close to our horizon over here. We're looking at it, but here we're looking at it under a big dark cloud, maybe a thundercloud or something. We're looking between the vegetation and the base of the thundercloud, and we're seeing the sunlight scattered from this parcel of atmosphere in the distance. So what does this look like? Before I show you, we could actually replace this dark cloud by the moon in a total solar eclipse. Exactly the same thing. We're shadowing the Earth by an opaque substance between us and the sun. So here's the moon hiding this path of light travel from us by shadowing the atmosphere. And we'll come to that in a moment. So this is a lovely picture taken by a colleague of mine, actually in Munich, of a rather spectacular thundercloud looking at the sun illuminating the distant horizon. And you can see the orange horizon. This is because of the extinction of that light on passing through all the atmosphere between the scattering and us. But here it's shadowed by the thundercloud. So we don't get any addition to the light that's scattered by this long horizontal path through the atmosphere. If we didn't have the cloud there, we'd be looking at something called aerial perspective. Here we're looking at distant ranges of hills across a lake, with a clear sky. And as we progress down the increasing distance of these hills, we see the increasing amount of blue sky in front of the distant hills. And this is very well known as aerial perspective, and it's very well understood by artists, of course. And the point is that we see this aerial perspective because the whole path between us and the distant hill is, of course, open to sunlight. So sunlight is coming down, it's scattering off the air between us and the hill and coming towards us. And because that's predominantly Rayleigh scattering, that's blue. So we see blue haze against the mountains. If we shadowed the sun and removed it from the lake surface, the light would look quite different. And I can show that. Actually, no, this is another. Actually, sorry, this was just another example of the aerial perspective, but this time at twilight, where it's the blue sky above you that's scattering off the range of the atmosphere between these hills at different distances and producing this lovely blue aerial perspective, even though the sky is partly colored. It's another observatory in Chile. Now, if we have an eclipsed sun in the center here, we're shadowing the atmosphere between us and the sun. And you can see the extent of this shadow. You can see the edges of the shadow around here. But we're seeing the phenomenon here, which is very similar to the light under the thundercloud. We're seeing the scattered light from the sun, the clear horizon beyond the shadow of the moon. We're seeing the light scattered towards us, suffering the extinction on the way towards us without having the blue light added to it. So the scattered light from the horizon is quite orangey here, whereas as you move out of the shadow, you can see the light becoming whiter and whiter because you have more and more contribution from the aerial perspective over here, the scattered light from the illuminated part of the atmosphere. And this is actually a simulation of the shadow over this is the northern coast of Chile up here. This is the northern part of South America. And so the shadow, the observatory is somewhere down here, and the shadow is blocking the sun. Now, I don't want to spend too much time talking about this, but I mentioned at the beginning about exoplanets and lunar eclipses. In a lunar eclipse, the sunlight is coming past the Earth. So the sunlight, the Earth is blocking the sunlight from the moon. The moon's in shadow over here. Some of the sunlight is grazing through the Earth's atmosphere. The thickness of the atmosphere is very highly exaggerated here, of course, but this is just a diagram for illustration. The sunlight travels through the atmosphere, gets refracted slightly by refraction in the atmosphere, hits the moon and comes back through the atmosphere, and we can observe it from here. So this is the way we observe a lunar eclipse. We're sitting on the Earth here, we look at the moon, we see the moon illuminated by light that's grazed past the edge of the Earth. And we can witness the colors of the moon. We can also measure the spectrum of the light coming from the moon, and that tells us a lot about the Earth's atmosphere. And indeed, this passage through an exoplanet transit, when a planet is transiting its parent sun, would tell us a lot about the content of the atmosphere. That's what we want to do. That's why we want to make those observations. And this is actually the decomposition of a spectrum taken of a real lunar eclipse, where the light was transiting the Earth just above the Antarctic coast south of Australia. So the light was traveling through the atmosphere above the Arctic coast, hitting the moon, coming back to the observatory, which was actually close to Beijing in China, and producing the spectrum. And again, we can see the huge absorption of ozone in the spectrum here. We can see the absorption from oxygen, molecular oxygen, in these red lines here. we can see absorption due to nitrogen dioxide in the atmosphere, which is probably a pollutant in this case. And all these, the molecular scattering and the aerosol scattering, all contribute to the color of the lunar eclipse. And I think you can see from this that when we do an exoplanet transit, the ozone is an enormously important absorber in the atmosphere. It's the only one we'll probably see clearly. Now, this was a lovely picture. You may have seen this picture. This was the Royal Observatory Greenwich's Insight Investment Astronomy Photographer of the Year Award 2019 was given to this person here. And I wrote to him and asked permission for him to use his beautiful picture, which is a time sequence of a lunar eclipse. You can see deep in the lunar eclipse here. You can see as you start moving out of the eclipse, it's getting much brighter then. He's compensated for that brightness in the way he's processed the pictures. But you see this lovely blue corner up here. This is when the light is traveling high in the Earth's atmosphere before it hits the moon, and it's traveling through the ozone layer, and it's colored blue by the ozone in the ozone layer. And then the Earth, the moon emerges from the shadow, and it becomes white sunlight again. So this transition from the deep red of the highly obscured moon, the light passing through the thickest part of the Earth's atmosphere, as you near the edge of the shadow, the light travels through the ozone layer and becomes blue. And I thought that was a really beautiful illustration. Okay, well, my final few moments is just to talk about the nighttime sky. And I'm talking particularly here to the people who are concerned with light pollution and the need to maintain dark skies, because as our planet becomes more and more polluted, it's harder and harder to see scenes like this. So these are pictures taken by our photo ambassadors in Chile. These are people working at our Chile observatories who are very keen on photography, and they take the most wonderful pictures of the Chilean sky from the Atacama Desert at the observatories. And there's a wonderful collection of those on the ESO website that you can look at. So this wonderful picture of the Milky Way, and this red air glow here comes from oxygen in the atmosphere for reasons which I'll explain in a moment. This is the air glow seen from the International Space Station. This is the Nile Valley down here, the Nile Delta. This is the air glow, which is rather restricted in altitude, and it changes color from red over here to green over here. All this air glow comes from the oxygen molecule, but the excited state in oxygen has slightly different lifetimes, and so they appear at different times of the night. The red emission is more prevalent just after sunset or just before sunrise, and the green is more prevalent deep into the night. And if you're looking up with a fisheye camera from the ground, again, you can see the air glow around the horizon very, very clearly, and you can see the color change at different times from the ground. Very beautiful. These are the transitions in oxygen. There are two red oxygen transmissions, and there's a green, the strong green transmission is here. There's also some yellow nitrogen emission as well in the air glow there. These are the same emissions as seen in the aurora, but actually it's quite a different process. The air glow is produced by ultraviolet light that hits the atmosphere during the daytime and gets stored as energy in the atmosphere until night, when it gets gradually re-emitted. So it's energy that comes from ordinary ultraviolet sunlight, whereas the aurora is emitted by the same atoms in the same way, but those atoms are excited by energetic particles coming from the sun and being guided by the Earth's magnetic field to hit the atmosphere in particular positions near the poles. So these are different phenomena, but they're the same kind of emission process. And you can see the wonderful change in colors here of the green and the red aurora. And I'll finish with this picture. which shows it all. But you might just want to notice that the joy we get in this dark sky, where you can see the Orion, the belt of Orion here, the Magellanic Clouds. Many of the astronomers here will know these very well. The joy of this is that it's 60 million times fainter than a bright sunlit scene on the planet. So we really need to protect our dark skies to enable people to photograph at least skies like this. It's a huge range in brightness, and it needs a lot of protection. So I'll finish there. Thank you very much for your patience. And where am I? I'm happy to answer questions.
Thank you very much. We'll take some questions now. We've got a couple in the chat channel from Roger Moses. The first thing he asks is, have you looked at the tapetum of the reindeer's predators, wolf, polar bear, or whatever eats reindeer?
Well, again, very good question. Yes, we've looked at the tapeta of many different animals, and mostly they appear a kind of turquoise with golden patches, and we do understand why that is. I'm happy to talk to you, Roger, about this at some point. What the reindeer does, it takes its the structure of the tapetum. The tapetum is made out of very fine fibers of collagen, and the spacings between those fibers are very, very small, about 200 nanometers. That's about half the wavelength of blue light. And that regular structure of collagen fibers makes what we call a photonic crystal. And that photonic crystal in the winter reindeer reflects blue light. And in fact, it reflects first order blue light. And what happens as the reindeer transitions into summer, it releases those collagen fibers and they float further apart, and it moves the first order spectrum into the near infrared. And so it has a long shoulder between the first order and the second order reflected spectrum. And in this shoulder, you see the fairly reasonable sort of silvery, turquoisey, golden reflection. And this is true, I think, that kind of reflection you find in the wolf's predators as well. They don't have that blue adaptation. The reindeer has the advantage.
Right. Charles Draper is asking, why is it that the color that we perceive as yellow represents such a small proportion of the visible spectrum?
Well, the colors you see as yellow, a small proportion of the visible spectrum. Well, actually, if you look at the visible range of the spectrum, it's not such a small proportion. Especially if you're looking at the spectrum dispersed by a grating, the yellow is a substantial part. But you get rather little discrimination in that area of colors because, as I mentioned before, the green and the red detectors are fairly close together, and so you get rather little discrimination. And I think that possibly results in the yellow appearing a rather small section of the spectrum. I'm not sure I've made a very good answer to that, but I'll think about it some more. The yellow does get absorbed at twilight anyway. It gets strongly absorbed by the ozone and water and other molecules in the atmosphere. So that can make the yellow appear a bit fainter. But I don't know. I think we'll have to argue about whether it's really a small section of the spectrum. Sorry, Charles, that wasn't a very good answer.
I'm just reading the next question. Bob, do you have access to the chat channel?
No, I don't. Oh, maybe I do now. I didn't. No, actually, I don't.
Okay, I'll read it out. in the image comparing sunrise and sunset in Chile with the crescent moon visible, one has a gradual blend of blue down to red. In the other, there's a thick band of red. Is this what you'd expect, or just an artifact in this image?
I think it's not an artifact in the image. It's the fact that the lower levels of the color and the brightness of the twilight sky is very strongly influenced by the number and distributions of aerosols, which are mostly in the very low atmosphere. So when you're looking out towards the horizon, especially over the sea, you will see a fairly strong contribution of scattering from aerosols. And also over the sea, you will get temperature inversions over the sea, which will trap aerosols below a particular layer. And I think what you're seeing in that picture, the sunset spectrum is over the Pacific Ocean, whereas the sunrise spectrum is over the Andes, and you're not actually seeing very low because the Andes get in the way. So you're not quite comparing like for like when you're comparing those two images. And anyway, the distribution of aerosols over the Andes will be very different from the distribution of aerosols over the Pacific. So the banded structure, I think, it depends very much on where the aerosols are, where the water vapor is, and where the temperature inversions are.
Yes, and Kerry Gregory, who's a gemologist, is fascinated by all this, she says, and wants to know where she could learn more about receptors in the eye and so on.
Well, there are many books about eyes. I wonder if I can find one of them. There is a book by Michael Land about animal eyes, which I've read. There are a number of books about eyes. There's possibly not the best one for you to look at, but that was one. One book that I can unhesitatingly recommend to anyone who has been interested in detail in this talk is a book by Gertz Herper called Why is the Sky Blue? It's actually translated from the German. It's very well translated, and it's also an extremely good book, and it's a wonderful description of the physics of blue skies. So I think it's one of the best books I've read about atmospheres and colors of all.
Well, thank you. Well, going back to Roger Moses, he asks whether it was a surprise to see the Earth blue due to Rayleigh scattering after the first, after manned space flights. I mean, did we expect the Earth to look as blue as it does from space?
If you look back at Earth from space, I mean, I've puzzled over this problem long and hard, and I think the Earth does look blue mostly because of Rayleigh scattering. The oceans are so dark; they contribute very little blue color to the planet. You know, it's the idea that the Earth looks blue because it's watery, I think is mostly untrue. I mean, it contributes a little bit to the blue. But the thickness of the optical thickness of the Rayleigh scattering around the Earth, especially away from the center, is quite significant. And I tell you one thing you can do. There are some images made by one of the relatively recent Japanese meteorological satellites, which has a large range of filters for looking at the colors of the Earth for meteorology. And they were able to fit the atmospheric components of their images to Rayleigh scattering and other things. And so they're able to subtract the atmosphere from the Earth color. And those are very illuminating. I mean, they do show that the Rayleigh scattering makes a major contribution to the color of the Earth, even though it seems, if you just look at a small fraction of the Earth, it doesn't look terribly significant. It adds a huge proportion of the blue light to the Earth. So how much of this was expected at the time, I don't know. I don't think people probably hadn't thought very much about it and hadn't really modeled that, but they do now, and it's very clear that the atmosphere is the dominant origin of the color blue.
Right. By the way, anyone is free to turn their audio and video on and ask a question directly. I can't see everybody at once. I'm in gallery view. It's 2 screenfuls, so I might not see you right away, but you can certainly feel free to do that. So, for example, the person whose initials are NAS has asked a question. Do you want to ask it directly? I'll read it out then. Some observers report good sensitivity in UV and others in IR. Have you ever looked at different sensitivities in human eyes?
I've certainly looked at sensitivities in my eyes over the time since I was a child to now.
I'm not quite sure I understand the question though, because I mean, we don't really see UV or IR at all, I would have thought. But
well, we can see a remarkable distance. Take the infrared first of all. I can see the A band in the atmosphere, which is what, 7,600, 760 nanometers. When I look at the setting sun through a spectroscope, that's about as far as I can see. If you look into the ultraviolet, we do know that the transmission of the lens changes quite substantially with age. And so young people do have very good ultraviolet sensitivity. I can certainly see the line at the mercury line at 365 nanometers with my eye, although it's difficult to know whether that's produced entirely by fluorescence or by direct detection of the UV photons. But yes, I mean, I guess a lot is known about how the sensitivity of the eye changes with age. And a lot is known about how the sensitivity of the eye changes between different animal species as well. Many animals have quite good ultraviolet sensitivity. But it generally is the ones that are not quite so interested in visual acuity. I mean, things like birds of prey don't see into the ultraviolet because they're much more interested in visual acuity, I believe.
right, we're just going to have one more question then, the last one in the list. That's from Charles Draper again. He asks if how bright is the air glow as seen from the Andean observatories? Can you see it with the naked eye?
Yes, Charles, you can certainly see the air glow quite well with the naked eye. It's just you don't see it in color because you see it with your rods. The Chilean observatories are rather special because they're close to what's called the South Atlantic anomaly, which attracts auroral effects. And so it's a problem for spacecraft orbiting over that area of the planet. I mean, Hubble has to switch off some of its equipment when it travels through the South Atlantic anomaly, but it does produce both enhanced intensity air glow and very rapidly variable air glow in the Chilean observatories. And when you compare those observatories with, for instance, Australia or the Northern Hemisphere observatories, the air glow behavior is really rather different. The details of the origin of the South Atlantic anomaly are still somewhat obscure. I think a lot of work has been done to try and figure out what the cause is, but at one time they were thought to be due to nuclear explosions in the atmosphere, but I don't think that's thought to be true anymore.
Right, well, it's been a really great evening. I think that we'll all be looking at the sky, sunsets, shadows under clouds, all with different eyes in the future, and there's a lot to think about. I'm also really pleased with how we've brought in plenty of people who don't normally listen to our lectures, and we've stretched right across continents. We have one person participating from Japan, for whom I believe it's 4:30 in the morning, or at least that was the time when the lecture started. I think that is that's really excellent, and I hope that we can do much more of this. If anyone wants to know anything more about mailing lists or how to get more information about these lectures than you already have, please email me. I'll put my email in the chat column, and I can put you on a mailing list or provide you with more information as you wish. But right now, let's thank Bob Fosbury very much for such a great talk.
Thank you.
Thank you.